Okay, so we've seen two lectures on Dedekind domains, and today I'm going to give the last one on Dedekind domains, which will be the last bit of things that we'll need, and then we can start working with these ideals and define the norm of an ideal and so on. So let me just remind you what we did last time. Last time I finished by proving this theorem, which was that in a Dedekind domain, every ideal can be factored uniquely into a product of prime ideals. And so I just want to note that I should maybe have set it up from before I get started today. I wanted to mention from last time. So using this theorem, I'm going to make the following notation, here I said I took an ideal and I factored it into prime ideals, and I said, well, these prime ideals might not necessarily be distinct, but I'll just say since multiplication of ideals is commutative, we will usually write something like you take your ideal A and you're going to factor it into, like, say, P1 to the E1 all the way up to like Pn to the En, where now with these PIs distinct prime ideals. Great, so I'm just somehow simplifying the notation. In the theorem, I somehow wanted to have all of the ideals split up because of how it worked for the proof, but in general, we're just going to allow ourselves multiplicity. So some prime ideal squared or something like this. Anyway, that's what I wanted to say from last time. So now I just want to give you some uses of having this this unique factorization. So one corollary from this theorem is corollary 3.3.17. This is immediate. What I'm theory is that if I have a number field and the ring of integers, I'm not sure why I keep writing this. It's always this. Then every ideal in OK can be written as a product of prime ideals. I should say written uniquely. And yeah, the proof is just immediate. It's just this follows as OK is a Dedekind ring or Dedekind domain. Dedekind domain. By what was the result? We had a result. I can't remember what the number of result is. Let's see. What was it? Theorem 3.3.2. 3.3.2. Okay. So we know that for rings of integers we can factor. This is the whole point why we looked at Dedekind domains, is because we knew rings of integers were one of them. And it turns out that for the proof of the main properties that we care about these ideals, it's true not just in this special case that you have a number field in a ring of integers. It's true for general Dedekind domains. So might as well work in this extra generality. Okay. So what can we do with this uniqueness of factorization? Well, here we can start somehow playing around with these ideals as if like when we play with the prime numbers for integers. So for example, we can define like greatest common multiple and least common divisor. So here I'm going to tell you how to do this. So 3.3.18. Again, this will work for any Dedekind domain. So let R be a Dedekind domain. And I'm going to take A and B ideals. So for the moment, these are just going to be ideals. We won't really work with fractional ideals too much unless we need to, because most of the time you can just transfer everything, all the questions, into ideals. So I take two ideals, standard ideals. Then we define, so the GCD, the greatest common denominator, the greatest common divisor, So we define the GCD of A and B as follows. So this is one like a definition you maybe recall from the number theory course. It's like it's just the proper analog. So I'm going to take the product over I of pi to ni. Oh, mi. I should say what the pi's are. So I'm going to let define GCD and LCM as follows. I'm going to first let me take my ideals and factorize them. I know I can do this. I can write this as product over I of pi to the ni, and I can write this as product over I, again, pi mi. By changing the mi's to be zeros or something else, and I can make sure that they have the same indexing set. So I can take them both to have the same indexes, and just for simplicity. Then the GCD is just you take the product of pi's and you just look at the minimum of the ni and mi. So you look at the smallest number. So for example, if you're doing this for like when you do for integers, if you want to find a GCD of two integers, you can factor them, and then just go through each factor and just take the smallest power of each one showing up, and they'll end up giving you the GCD. So this is something hopefully you recognize. And then the LCM, the least common multiple of these two ideals, is the same thing, but instead of min, you take max. The maximum of ni and mi. Great. So once we have this factorization, we can define this LCM and GCD. And I should maybe mention here the pi are all distinct. So I'm using this for factorization. So why does this? Well, we'll see later why this has the right to be called GCD, or maybe we'll see more of this in the exercise in the problem sheets. But here's a proposition which somehow tells you how these things are related to usual operations and ideals. So you have proposition 3.3.19. So the R be Dedekind domain. And I'll take A and B ideals. Then the GCD of A and B is nothing more than the sum of the ideals, and the LCM, the least common multiple of A and B, is nothing but the intersection of these ideals. Great. And one of the exercises in the problem sheets will be to check that this does have the right to be called GCD. So it's like the greatest common divisor. Like there is a way of turning this definition of GCD into like the biggest ideal, which divides the ideal, or something like this. But here's a proof of this proposition. So proof, first of all, by corollary 3.3.14, we know that the division of ideals turns into containment. So yeah, if P divides A, then it means that A is contained in the ideal containing if the ideal P divides the ideal A, that means that the ideal A is contained in the ideal P. The greatest common divisor of A and B is the smallest ideal containing both A and B. Which, if you recall from the first lecture, the first problem sheet, which by definition is A plus B. Maybe I should say, so this bit, let me just, but this is the smallest ideal. This interpretation, I'll say this will be done in the problem sheets. Maybe by the time you're looking at it, it's already been done in the problem sheets. I don't think I'm the one that proves it. I'm sure this is one of the problem. I left it as a problem sheet question, but we'll see. In any case, this various common divisor should be the biggest thing that divides A and B, which somehow should be the smallest. When you think of division turning into containment, it should be the smallest ideal containing both A and B, which is by definition A plus B. Similarly, the LCM becomes the the largest ideal containing both. Both A and B, which by definition is just the intersection of the ideals. If you have a think about this, nothing. Yeah, this has to be a largest ideal. So yeah, you'll see a bunch of exercises to play around with this GCDs and LCMs to see that they do have the right definition. But this definition here that I've given you should. This definition, yeah, if I gave it to you for integers, this would work. So this is a good enough justification to why this works like this. And next, I'm not going to prove this, or you can see the kind of proof in the notes, but we're going to need this. Is going to remind you of the Chinese remainder theorem. So next, let's recall the following. I'm going to state it, and then we'll use it in the next result. So theorem 3.3.21. This is called the Chinese remainder theorem. And I'm going to state it for general ring, so let R be a commutative ring. This is the generality in which you can use it. That would be a commutative ring. And I take two ideals, A and B, co-prime. Yeah, I remember that this means that A plus B is the whole ring. It's just ideal by one. Then if you take the ring and quotient out by the product of these ideals, this is isomorphic to R quotient out by A times R quotient out by B. Great. So proof, you can see the notes, or maybe I'm sure you've seen this in some other course. Proof, see the notes. It's not something that we're going to worry about proving. It's a standard result. And I'll just remark that if you just use induction, then you can just extend this to having several pairwise co-prime ideals. But the reason I'm mentioning this is for the following theorem. 3.3.23. So it somehow tells us what all the ideals in a Dedekind domain, what the maximum number of generators any ideal in a Dedekind domain needs, in which case in this case it's 2. So let R be a Dedekind domain. And A an ideal. Then it's quite powerful. And for any alpha in A, so when I say ideal, most of the time I'm just going to, as usual, I mean proper ideal, so non-zero. If I take some alpha in A, I should just say it, so A proper. And for any alpha in A with alpha non-zero, so if I pick some element in there non-zero, we can find some other element beta in A such that the ideal, this ideal is just the ideal generated by these two elements. So if I have any ideal, I can pick any element inside of it at random, non-zero, just pick it, and then from that one I can find some other element inside the ideal such that together they both generate ideal. So at worst, if I want to describe an ideal in a Dedekind domain, or in like a number field, in a number, in a ring of integers, then I only ever need two elements to completely determine an ideal, which is quite useful. So my ideals always have like a generating set of size 2, at most 2. And this is quite useful for us studying our ideals. So let's do the proof. So given alpha, we will find, so we will construct a beta. So how are we going to do this? So we're going to do this by, we will find a beta such that this ideal is the same thing as the GCD of two ideals generated by alpha and beta, which by the result I told you before, this is just the sum of the ideals, which by like one of the first problem sheet, like I filmed the first problem sheet, the sum of the two ideals. So one of the questions, maybe it wasn't the assessed question, but one of the questions there gives you this. So I'm going to find an ideal, an element beta such that the ideal it generates it has a property that it, the GCD of that and alpha is ideal A. So how do we do this? So I'm going to let me take my ideal A and we factor into prime ideals. So P1 to the N1, PR to the NR, with PI distinct, these PI's distinct prime ideals. Since alpha is contained, alpha is an element of A, so the ideal generated by alpha is an A. We have alpha is contained in all of these ideals for all I. How I think of why that is the case? Well, each of these ideals divides A, which and then containment turns in, division turns into containment, which means A is contained in all of these ideals, prime ideals. And so since alpha is an A, then this ideal has to be in all of them. So in other words, yeah, so we have this, i.e. Pi to the Ni divides alpha for all I. So if we think of what the factorization of this ideal generated by alpha is, these PI's to the Ni are going to show up, but there might be other things. I've not said that this is everything. There might be other prime ideals. So let me give these things a name. So now I'm going to let, say, Q1, QS, be the other prime ideals. Dividing alpha, this ideal, if any, yeah. There might not be any, but there could be some. So we have following. So what I've said is that this ideal has to be divisible by all this PI's to the Ni. So I have this factor when I factorize it, and then I'm going to split up into two things, and I have QJ, a bunch of ideals QJ, and let's not bother with making them distinct. Let me just write them like this for now. So now I'm going to construct my element beta using using these QIs and the Chinese remainder theorem. So we have this factorization. So we construct beta as follows. So we take, say, some beta I in this ideal, so this quotient. So this is P to the, not quotient, sorry, this is different. I take an element beta I, which is in this Pi to the Ni, but it's not in Pi to the Ni plus 1. So it's in this ideal, but not in this ideal. Think of it as like, the ideal P is contained inside the ideal, contains the ideal P squared. So I can find elements in P which are not in P squared, for example. So I'm going to take elements like this, and then by the Chinese remainder theorem, which was 3.3.21, we can find some beta in R such that beta is congruent to beta I mod p to the I n I. Let me just recall this IE. What this means is that beta minus beta I is an element of p I n I. This is what I mean by mod. This is what mod means. Just means that the difference lies inside this ideal. So I can, what the Chinese remainder allows me to do is, like, I have all these elements beta I can find some element, and these are like lying in some ideals. I can find some big element beta of R, which is congruent to each of these things mod p to the ni for I in, say, 1 to R. The first R here, this is the product from I equals 1 to R. This is the product from J equals 1 to S. And then I can make it such that it's co-prime to the other one, so it's congruent to 1 mod Qj for J in 1 to S, so for the other ones. So each of these elements is exactly in this ideal, but not in any ideal smaller. And these beta J's are just in the first, are just one inside these QIs. Which we can do. I'm just going to note that we can do this. So remember, for the Chinese remainder theorem, we had this condition about the ideals being co-prime. So we can do this since these PIs and QJs are pairwise distinct by construction, and because they're distinct prime ideals, we must have that QJ plus PI to the n I is the whole thing. So QJ is a prime ideal, so it's maximal. So when I take a maximal ideal and add any other ideal to it, it has to give me the whole ring. Well, as long as it's a different ideal, it has to give me the whole ring because of maximality. Otherwise, this would be another ideal which contains QJ, but QJ is a maximal ideal. Remember, in Dedekind domains, all prime ideals are maximal. So, and we have this for all I and J. Moreover, we have that Pi to the Ni plus Pj to the Nj. So this is for how the Q's and the betas, the Q's and the P's behave against, how they relate. And then between the PIs and the PJs, we notice that this is just a GCD by our previous result of Pi to the Ni, Pj to the Nj. But because these are different ideals, we know that this is just 1 by, 3.3, but just by definition from 3.3.18. So this element beta that I've constructed, if I think of how I factor this ideal, then it has factors Qi, Ni, and then it doesn't have any factors in the QJs. So by definition, just by definition for GCD, definition 3.3.18, not 38. This gives us, we get the GCD of this thing is the GCD of these GC is the product is just 1 to R of Pi to the Ni, which we said is exactly A, and therefore beta has to be some element in A. Think of why this is the case, we're done. So which finishes the proof. Great. So I've originally, remember, I took my beta to be some element of R by the Chinese remainder theory, and it existed. But now I know something about its factorization, or how its ideals compared to alpha. And so now I have this sort of relation, and so from this expression that I wrote up here, this means that this element beta has to be inside of A, and then now I've taken my element beta from knowing that it was an R, and now I know that it's an A, and then I know that it has this property, which is exactly what I was looking for. So we're done. Cool. So every idea is generated by two things. What's another consequence of this unique factorization? It's the following, and this is going to be the last thing for this lecture. Here's Theorem 3.3.24, which says Dedekind domain is a unique factorization domain, so a UFD, if and only if it's a PID. So one direction of this we know just from like basic ring theory. So if R is a Dedekind domain, that is a PID. We know that PIDs always imply UFD. So by proposition, this didn't have anything to do with being a Dedekind domain. It's just general fact. By proposition 1.2.6, it's a UFD. This is a proposition I didn't prove, I don't think, but it's just a standard algebra thing that we can assume. So any PID is always a UFD. So we just need to prove the converse. And now here we will use that. This isn't true in general, but here we are going to use that we're using it, that we're working with the Dedekind domain. Now, let R be a UFD. And assume for condition it's not PID. Great. So then, by theorem 3.3.15, there must exist at least one non-principal ideal in here. Just to remind you what this said, that this said that every has must have one at least one non-principal prime ideal. It's a claim. Yeah. So I'm assuming it's not a PID. So not every ideal is principal. So there has to be some ideals which aren't principal. And now, because we're in a Dedekind domain, we know that any ideal is always factorable as a product of prime ideals. And so if all of my prime ideals were always principal, then a product of principal ideals is always principal. So then, because then I wouldn't be able to have a non-principal ideal. So at least one of the prime ideals has to be non-principal. Just one of them has to exist. And so there must be one non-principal prime ideal, call it P. So I'm gonna let S, this is like a standard trick by now, S be the set of all non-principal ideals, such that something, so let S be the set of all ideals A, such that A times P is principal by theorem 3.3.5. We know that S is non-empty. That was this theorem that told us that for any ideal, I can always find some other ideal such that their product is principal. So there is at least one element in S. So by the usual Noetherian trick, we can find a maximal element. So so using Noetherian, we can find a maximal element in here. I'm going to call it M for maximal. So I'm going to let, this is a maximal in this set, so it means that M times P is principal, so I'm going to call this alpha. So I'm going to let MP be alpha. I claim that this alpha must be reducible. Let's assume this for the moment, and then we'll come back to this. So I'll assume this for now. Assume this for the moment. If we take, say, some element in the difference, so in P, take away this ideal alpha, which you can do. And this means that alpha is contained in the ideal P. This is what this P divides alpha, so alpha is contained in the ideal P. So I can find some element in here, and I can find some element B in the other difference of M and alpha. So I'm going to say what you can do in the first case, the reason that P isn't generated by alpha is because the ideal is not principal. So this ideal P is not principal, so there has to be something in it that's, by assumption, we're assuming it's not principal. So there has to be something in here which is not in any ideal alpha, because otherwise it would be principal. So what you can do in the first case, as P is not principal, and in the second, so this will just follow some exercise. What was exercise 3.3.6? Then I take these two elements, then their product is an alpha, but this means that alpha divides A times B, but by construction, so the product of them is in the ideal generated by alpha, by how I've constructed it. Yeah, this is an element in P, this is an element in M, and M times P is alpha, so the product has to be an alpha. So I have this. What does this mean? This means that alpha divides AB, but by construction, I've taken A to be in P not alpha and B to be in M not alpha. So I know that alpha doesn't divide A and alpha doesn't divide B, and this can't happen in a UFD. So in a unique factorization domain, you can't have some element alpha dividing two things, the product of two things, and not dividing one of them. This is one of the things of making things something a UFD. So I just need to come back and prove my claim, which is, my claim was that alpha must be an irreducible element. Oh yeah, so here I'm using alpha is irreducible. So if alpha divides A times B, then alpha has to divide A or B. This is what happens in a UFD. So need to prove alpha is irreducible. So note that if we had a factorization, so if alpha was beta times gamma, then one of these, the ideals that they generate, so one of beta or gamma, one of these two ideals would be of the form P times some ideal B for some B dividing M. So these ideas would have to be divisible by P. So I've taken this element alpha. If I factor it, I have this this equality here. So if I take some element in this alpha and factor it, then the factors of each of these ideals, one of them is going to have a factor of p showing up. But now, and b is some ideal dividing m, but this ideal m is maximal. So b equals m, therefore one of these two things is a unit. Well, one of beta and gamma is the ideal generated by 1, which is a whole ring, so it's a unit. Okay, and that finishes the proof. So, great. Now in Dedekind domains, we have some very useful tools, which somehow basically mean that we can work with ideals somehow as we would work with numbers in the integer. So you take an integer and you always want to factor it into prime numbers and work with that. In rings of integers, this might not be the case. You might not be able to factor things uniquely into prime or into irreducible elements, but we can always factor things uniquely into prime ideals. Then we can play with these prime ideals somehow like we would play with prime numbers. So I've just defined the GCD and so on. Cool. So this will end us for our series of lectures on Dedekind domains. We'll probably still have some results on Dedekind domains showing up later on. But now I'm going to move towards, now that we have all of this basic setup on Dedekind domains, we're going to start talking about norms of ideals and so on. And this will be very useful for us understanding the structure of ideals in these rings of integers. All right, so I'll finish there.